13,800 million years ago, what we know as our universe began with the Big Bang, an extremely hot and dense event, but that at the same time expanded and cooled. It was composed of matter, antimatter, and radiation. The volume of our observable universe has grown to reach a radius of 46,000 million light-years at present, and the limit of what we can measure corresponds to the light that reaches our eyes currently. Although that distance is enormous, it is not infinite, but simply the limit of what we observe. What lies beyond? What about the non-observable universe? Is it possible to determine if the universe we live in is finite or infinite? That is there an end to what we call the universe, or is it infinite beyond our measurements? In this documentary, we embark on a journey beyond the known, delving into the realms of theoretical physics and mind-blowing concepts, exploring the mysteries of what could exist beyond our cosmic door. To answer the question of what is outside the universe, we first have to understand exactly what we mean by universe. Have you ever wondered how vast the universe is when you look up at the night sky? What if I told you that it is so big that we cannot see everything? The observable universe is the region that we can see. We are located in the center of what appears to be a huge cosmic bubble. Let's delve into the fascinating world of the observable universe and see how big it is. If you went outside right now, you could only see as far as your sight reaches horizontally. Your vision would end up reaching the horizon. Beyond that, you couldn't see much, but you must be aware that there is life beyond the horizon. There is more on this planet than you can see. Also, when you look 360 degrees around you, it seems that you are in the center of the world, although you know that is not really the case. That is how it looks from any point on Earth. In the same way, our vision of the universe is limited to what is visible to us on Earth, and it is probably infinite in size. We can only see as far as our cosmic light horizon reaches, because we cannot see the entire universe. It may seem that we are the center of the universe, but this is just an illusion. Light, which travels at a fast but finite speed, simply has not reached us from more distant parts of the universe. Therefore, the entire universe and the observable universe are very different. Everything that we have seen or been able to see until now is the observable universe. On the other hand, everything that exists, existed, or will exist is called the entire universe. More specifically, the observable universe is the region of space visible from Earth. The term observable, in this context, does not mean that there is something detectable, nor does it apply to the ability of modern technology to detect light or other information from an object, but refers to the physical limit defined by the speed of light. There is no signal that can move faster than light, because such signals could not reach us. However, there's a maximum distance, known as the particle horizon, beyond which nothing can be observed. Astrophysicists sometimes distinguish between the visible and observable universe. The former includes signals from the end of the inflationary epoch, while the latter includes only signals emitted since recombination. But how are distances measured in space? Astronomers use different techniques to measure cosmic distances. Basic trigonometry can be used, similar to that studied in high school math class, to measure things that are quite close, such as those in our solar system and even in our small neighborhood of the Milky Way, less than 100 light-years away. With the help of the parallax method, the distance of distant objects can be estimated. When you look at your finger with your left, while closing your right, and then look at your finger with your right, while closing your left, you will notice that the position of your finger appears to change with respect to a point on the wall. This is parallax. By measuring this small change and knowing the distance between your eyes, you can calculate the distance to your finger. It is trigonometry. When it comes to measuring distances to other stars, there are no two eyes that can do the trick. Instead, the Earth's orbit around the Sun provides the baseline for these calculations. Simply, if you take the position of a star once a year at a point in the sky, and then again 6 months later, you will have a relative position of the nearby object in relation to the more distant stars in the sky. Thanks to the Pythagorean theorem, you can determine the distance if you know the size of the Earth's orbit and the angle of light in those two measurements. However, the displacement of a star decreases with distance, making it difficult to measure this angle and requiring the use of a more advanced method. Once trigonometry is no longer useful, astronomers look for Cepheid stars, which are extremely bright and common. These specific stars were first identified in 1794 and can pulse, becoming fainter and brighter in predictable cycles. Surprisingly, the longer it takes a star to pulse, the brighter it is. Similarly, the shorter the duration of the pulsation, the fainter the star is. These pulsations are directly related to their absolute luminosity, which occurs in well-defined and predictable periods of time, ranging from 1 to 100 days, just as if you saw a candle right in front of you and another far away. The one that is closer would seem much brighter, and therefore, the actual brightness of those stars can be determined and, consequently, their distance by measuring the nearby Cepheids and comparing the duration of their pulsation period with that of the more distant Cepheids. The Cepheid variables can be seen and measured at a distance of about 20 million light-years, compared to a maximum distance of about 65 light-years for parallax measurement from Earth and just over 326 light-years for the ESA's Hipparcos mission. It can serve as standard distance markers, which constitutes another crucial step in the micrometric distance scale. Although 20 million light-years seems like a huge distance, the cosmos is 1,000 times larger, so we need to add another step to the scale. This is where supernovas, especially those of specific binary star systems, are useful. One star of these binary systems dies and becomes a white dwarf, while the other continues to exist. Next, the white dwarf begins to consume the surviving star and grows larger until it reaches approximately 14 times the mass of the Sun. At that moment, a huge explosion occurs that releases more energy than entire galaxies and is visible in over half of the observable universe. We call this a Type 1a supernova. Astronomers can determine the absolute brightness of the explosion and, consequently, the approximate cosmic distance to those distant galaxies, since we know how much mass is exploding at even greater distances, tens of billions of light-years away. Here, the Hubble constant comes into play, named in honor of Edwin Hubble, which is the unit of measurement for the expansion of the universe. This is where things start to get a little complicated. The universe has been growing since the Big Bang began its expansion. Some Music 1,382% suggests that there is something there that is causing the growth to slow down. This could be dark matter, which is invisible to conventional instruments. However, if growth increases, dark energy may be driving expansion at a faster rate. The observation by the astronomer Harlow Shapley in 1929 suggested that galaxies appear to move away from the Milky Way. Hubble discovered that the farther these galaxies are from Earth, the faster they appear to move. Although it was previously thought that this phenomenon was due to the receding of galaxies, astronomers now understand that what is really seen is the expansion of the universe. The same phenomenon would be observed at the same speed throughout the universe, since better and more sensitive telescopes have been used to perform the measurements. Hubble's original calculations have been confirmed over the years by observations recently made by various telescopes. The universe is expanding at different speeds, depending on where you look. The Planck telescope measures the expansion of the farthest universe, which is expanding at a slightly lower speed, for 116 meters per second or 67 kilometers per second per MEAP park, compared to the Hubble Space Telescope and the Gaia Space Telescopes, which measure the expansion of the nearby universe at 456 meters per second, 735 kilometers per second per megap. Bach. It may be difficult to imagine, but not only is the universe expanding at an ever-increasing rate in all directions at the same time, but the space between the objects in the universe is also expanding. Everything is moving away from everything else faster and faster. This expansion and acceleration between objects is related to dark energy, which goes beyond the topic of this discussion. So the farther you look, the faster the galaxies move away from us. The galaxies that are very far away can be measured in distance by measuring their redshift, which tells us how fast they are receding from us. Astronomers use redshifts to measure the expansion of the universe and, consequently, the distance to the oldest and most distant objects in it. But what is a redshift? It is often compared to the high-pitched sound of an approaching ambulance siren, which becomes lower as it passes and eventually moves away. The reason behind the change in the sound of an ambulance is the phenomenon known as the Doppler effect, an excellent comparison because the waves that are affected by their movement through space and air carry both sound and light. Sound travels through the air at a maximum speed of 750 miles per hour or 1,200 kilometers per hour. Sound waves in front of an ambulance are compressed as it moves forward and sounds its siren. Meanwhile, the sound waves behind the ambulance begin to propagate. This means that the frequency of the sound waves is higher in front of the ambulance, which means that more sound waves will reach the listener's ear, and lower behind it, which means that fewer sound waves will reach the listener's ear during a given period of time. Our brain interprets pitch changes as variations in the frequency of sound waves, similar to light. Light is a wave that moves at a fixed speed of 186,000 meters per second or 300,000 kilometers per second, about 1 billion km/hour. So light follows the same rules as sound. Galaxies, as we know them, move away from us in a similar way to how an inflated balloon would cause a wave created in its fabric to stretch. The wavelength of light stretches when galaxies move away from us. By using a prism or a suitable telescope, such as diffraction gratings, we can see a series of absorption lines of elements such as sodium and hydrogen. However, all those absorption lines undergo a Doppler shift and shift towards the red part of the spectrum. If that galaxy is moving away from us, we call it redshift. The opposite occurs with galaxies that are approaching us, which are blue shifted. Astronomers usually only use the term redshift to simplify things. If a blue shift occurs, they simply place a negative sign in front. The redshift of a galaxy increases with the distance of the galaxy from Earth. As a result, the redshift of a galaxy on the cosmic horizon, the outer edge of our observable universe, is almost infinite. This indicates that the light coming from that distant galaxy has very little energy, so we can barely see those galaxies with a visible light spectrum. When Hubble observed the light of distant galaxies through a prism, he observed a redshift away from the known variable for color. Hubble discovered that almost all the galaxies he examined had this redshift, indicating that they were moving away from us at an extremely great distance. The distances of galaxies can be determined quite accurately by plotting various redshifts and known distances on a graph. Music, this is the ultimate measurement tool and basically serves as a reference for distances in the universe. The remaining radiation from the Big Bang, or the moment when the universe originated, is known as the cosmic microwave background. According to the theory, the cosmos experienced rapid cooling, expansion, and inflation during its birth. The cosmic microwave background represents the heat that remained after the Big Bang. The cosmic microwave background is present throughout the cosmos, but is invisible to the human eye because it is very cold, only 2,725 degrees Celsius above absolute zero, or minus 27,315 degrees Celsius. So, it is invisible to humans. This indicates that its radiation is most perceptible in the microwave region of the electromagnetic spectrum. The cosmic microwave background dates back to about 400,000 years after the Big Bang, and, as we all know, the universe began 138 billion years ago because the temperature of the universe was extremely high in its early stages, when it was only 1/100th of what it is today. The atoms that existed then rapidly split into protons and electrons, which are tiny particles. The electrons scattered the CMB radiation in the form of photons, which are particles that represent quantum states of light or other radiation types. Just as optical light propagates through a thick fog, photons also traveled through the early universe. The universe was cold enough for hydrogen to form about 380,000 years after the Big Bang. The CMB photons move in a straight line because collisions with hydrogen barely affect them. The point at which the CMB photons last collided with matter is known as the surface of last scattering. Beyond that point, the universe was too large, which means that when we map the cosmic microwave background, we're looking back in time to 380,000 years after the Big Bang, just after the universe became opaque to radiation. In 1948, American cosmologist Ralph Alpher made the first prediction about the CMB while collaborating with Robert Herman and George Gamow. The group study focused on Big Bang nucleosynthesis, or the synthesis of elements other than the lightest isotope of hydrogen in the universe. This type of hydrogen occurred very early in the history of the universe, but the discovery of the CMB was accidental. Arno Penzias and Robert Wilson, two researchers at Bell Telephone Laboratories, were developing a radio receiver in 1965 and were perplexed by the noise it emitted. They quickly discovered that the noise came from all directions of the sky, from the empty space between stars. This radiation is the oldest and farthest that has been found so far, which essentially means that the farthest we can see in time is 138 billion years, since it took 138 billion years to reach us 8 billion years, since light has taken 138 billion years at the speed of light to reach us. Therefore, the observable universe has a radius of 138 billion light years. Furthermore, regardless of the direction we look, the light we see has only traveled for a maximum of 138 billion years, since the universe is only about 138 billion years old, and it takes time for light to travel through space. Given this, it would be logical to assume that the observable universe would be 2 by 138 light-years wide. However, this is not correct, since space has been expanding over time, pushing distant objects that released that light 138 billion years ago even further away from us. Let us remember the Hubble constant and how it was used to measure the expansion of the universe. The universe has been expanding for the 138 billion years that the light from the CMB has been traveling towards our eyes, pushing the edge of the known universe even further away, although humans are not technically able to see that far. The current location of the origin of the photon, determined by the Hubble constant, is at the astonishing distance of 46 billion light-years, so the diameter of the observable universe, calculated by multiplying by 2, is 92 billion light-years. It is evident that calculating distances of this magnitude can confuse the mind, beyond the realm of human understanding. Fortunately, with the cosmic distance ladder and a large number of astronomers expert in this type of measurement, we can understand how the universe moves, as well as our place in it. By adding all the galaxies of this region of space, we would discover that our observable universe contains the astonishing figure of 2 trillion of them. One might think that there would be no upper limit to the amount of universe that could be seen if we waited an arbitrarily long time, and that we could see an arbitrarily vast distance. But in a universe with dark energy, that is simply not the case. Dark energy is expanding the fabric of space at such a rate that GNZ11, the high redshift galaxy, is moving away from us at an estimated rate of 426,000 kilometers per second, more than twice the speed of light. The most distant objects will appear to gradually disappear from our perspective as time passes in a universe driven by dark energy. There is always more to discover in the universe, but the amount that humans can observe is finite. We can determine what we call the future visibility limit, or the farthest distance that humans will be able to observe based on the rate of expansion, the amount of dark energy we have, and the current cosmological parameters of the universe. Our current vision limit is 46 billion light-years in a universe that is 138 billion years old. Our maximum visibility in the future will be approximately 33% greater, 61 billion light-years. There are currently galaxies whose light is heading towards our eyes, but have not yet had the opportunity to reach us. There are more galaxies to discover than there are in the visible universe, which might surprise us if we added up all the galaxies in the regions of the universe that we will one day see, but that we cannot access now. Music. In addition to the 2 trillion galaxies that are currently visible to us, there are another 200 billion galaxies that are not visible in the Milky Way, the galaxy in which the Earth is located, and that are not visible in any other galaxy, but that we cannot access now. Music. In addition to the 2 trillion galaxies that are currently visible there are another 27 trillion galaxies waiting for us to see them. Our measurements of these phenomena would indicate whether the universe has a finite size and an edge, or whether its properties begin to change as we look at more distant distances. The unobservable universe is at least 250 times larger than the currently visible part. We will never be able to observe anything that comes close to those great distances. In the future, we will be able to see objects at a distance of up to 61 billion light-years, but no further. This will reveal something more than twice the amount of universe that is currently visible to us. Conversely, the unobservable universe must have a diameter of at least 23 trillion light-years and include a volume of space more than 15 million times greater than what is visible to people here on Earth. However, when we consider the universe beyond our current observation limit, it is important to keep in mind how little of that universe we can actually reach or explore. Everything we're looking forward to seeing depends on the light that was already released billions of years ago, precisely at the time of the Big Bang. As things stand right now, humans could not reach almost any of the galaxies in space, not even if we fled at the speed of light. Not only is the universe expanding, but distant galaxies appear to be moving away from us more rapidly because of dark energy. The limit of what we can observe today is much less than the 47 trillion galaxies that we will ultimately be able to observe up to a distance of 61 billion light-years. In other words, there will be 47 trillion galaxies that we will ultimately be able to observe up to a distance of 61 billion light-years, 7 trillion galaxies that we will be able to observe in the future at a distance of 61 billion light-years. In other words, there will be 47 trillion galaxies that we will be able to see in the future. Not many of them will see us as we are now, and most will only see us as we were in the very distant past. Of all those galaxies that we will one day see, 4,634 trillion are currently unattainable, even traveling at the speed of light. Someday, in the distant future, they will reach our eyes as time passes and the light of the last resistant galaxies continues its inevitable journey towards us in the expanding universe, ever closer to our ultimate cosmic point of view. All of this contributes to our understanding of the night sky. The theory of the expanding universe also contributes to understanding why our night sky is dark and how it relates to the observable universe. Now, what about the center of the universe? After all, we are the center of the observable universe, since this is limited to the space visible from Earth. We are at the center of it, and just as the view from a very high tower is a circle centered on the tower, the space we can see from here is naturally centered here. To be more exact, each one of us is the center of our own observable universe, but that does not imply that we are the center of the universe as a whole, just as the tower is not the center of the Earth up to the horizon, but rather it is the center of the part of the world that you can see, which does not mean that there is nothing beyond, simply because we cannot see beyond the horizon. In the same way, the observable cosmos is no different. When we look at the sky, we observe light from matter that is currently 46,000 million light-years away, and with a maximum age of 8,000 million years, but beyond that there should be much more universe, beyond the limits of what we can see now, the unobservable universe. Our field of vision of the universe is expanding exponentially. All we have to do is observe and wait for the universe to age and the light from more distant places to reach us. Despite all the measurement techniques, the actual size of the universe remains uncertain. It could be infinite, and parts of it remain outside the observable universe because they're too far from Earth or our equipment for us to have received any of the light emitted since the Big Bang. Although the European Space Agency has drawn up detailed maps of the oldest light in the universe thanks to the Planck Space Project, the size of the cosmos is still far beyond our understanding. According to the theory of inflation, the universe could be infinite and the visible universe only a small part of it. The size of the universe is also determined by its shape, which can range from a closed sphere to an infinite flat surface. The theory of general relativity, according to which space itself can curve, allows the universe to take one of three forms: flat like a sheet of paper, closed like a sphere, or open like a saddle. The fate of the universe depends on this cosmic geometry. The shape of the universe provides information about both its past and its future. For example, it can reveal whether the universe is infinite or finite, and whether it will continue to expand indefinitely or eventually collapse. For such a momentous question, its components are surprisingly simple. The density and rate of expansion of the universe are the only two parameters that determine its final structure. Dark energy constitutes approximately 68% of the universe, while dark matter constitutes 27%. Planets, stars, and other bodies are composed of normal matter, which constitutes the rest. The amount of matter contained in a specific volume of space is called the density of the universe. The universe can curve into a ball if its density is high enough to overcome the force of expansion through gravity. This is known as the closed model due to its spherical positive curvature. A mind-blowing property of this universe is that it is finite, but has no limits. However, space will warp in the opposite direction if the universe has a low density and is unable to stop expanding. An open universe with a negative curvature similar to a saddle would be created. According to scientists, the most likely possibility for the universe is the Goldilocks scenario. Most cosmological data suggest that the universe extends in all directions without curving positively or negatively, and that its density is around 6 protons per 13 cubic yards. In other words, the universe is flat. Perhaps this will serve as comfort to anyone who is disappointed by the roundness of our planet. Current observations and measurements of the curvature of the universe also indicate that it is almost perfectly flat. This may lead one to think that the cosmos is infinite. However, it is not so simple. It is not necessary for the universe to be infinitely large, not even in the scenario in which it is flat. Consider, for example, the surface of a cylinder. It is geometrically flat because parallel lines drawn on the surface remain parallel. That is one of the definitions of flatness, and yet it has a finite size. The same could be said of the universe. It could be completely flat and yet closed on itself. But what does a flat universe mean? Although this flatness is not the typical two-dimensional type that we see in everyday life, there are some examples that can help you imagine it. Imagine yourself in a square room, standing in a corner. Turn 90 degrees after moving 3 meters along the wall to the next corner. Take 10 more steps and turn another 90 degrees. Once you have finished 2 more of these, you will find yourself back at the beginning of the square. We all studied Euclidean geometry in high school, and adding an additional dimension results in a flat universe. However, the results would be different if this experiment were carried out in a space with positive curvature, which is a representation of a closed universe. In the example of the closed world, only 3 turns are needed to return to the starting point, while in the example of the flat universe, 4 are needed. In case you are still not clear, here is another illustration. 2 rockets traveling close to each other in a flat universe will always remain parallel, unlike a closed universe, in which the trajectories of these 2 rockets will separate, follow the curvature of space, and eventually turn around to meet at the starting point. In an open universe with a negative curvature, the rockets will separate and never cross again. The cosmic microwave background, or the glow of the Big Bang that radiates towards us from all directions, contains the best clues about the structure of the universe. Scientists have been measuring temperature variations in the CMB for several decades, performing trigonometry on the largest scale imaginable, and have found virtually no curvature. A flat universe is a key piece of the standard cosmological model, also known as the lambda cold dark matter model, LCDM. Lambda is the Greek letter denoting dark energy. Another proof of flatness comes from Baryan acoustic oscillations, which are the traces of primordial sound waves left in the galaxies after the Big Bang. As we continue to explore and map the cosmos, the immensity of the universe serves as a humble reminder of our place in it. The actual size of the universe may remain one of the greatest mysteries of science, although we may be closer to making more accurate measurements. Let's make a comparison between the size of the observable universe and some more recognizable things. The observable universe is so large that about 1 septillion Earths, a 1 followed by 24 zeros, could fit inside it, which is equivalent to more Earths than there are grains of sand on all the beaches in the world. It could be assumed that the observable universe must be densely populated with matter, given its enormous size. Well, that is not the case. It is believed that the observable universe contains several 100 billion galaxies, and that there are billions or possibly trillions of stars in each of these galaxies. However, in reality, most of the observable universe is just empty space. It is most likely that if you pick a random spot in the observable universe, you will end up in empty space instead of near a star or galaxy. In reality, we're looking back in time when we look toward the observable universe, because light takes time to travel the distance separating us from a star or galaxy, and the time it takes to reach us increases with distance. Therefore, the observable universe is not only a place, but also a record of cosmic history. The fact that we cannot see beyond our cosmic horizon does not mean there is nothing there. As if the mysteries of dark matter and dark energy were not puzzling enough, another cosmic puzzle has been discovered. Astronomers have observed that entire groups of galaxies travel in sync toward a single point in the sky. Researchers even speculate that a force beyond the observable world could be responsible for this unexpected movement, which does not appear related to the expansion of the universe. The finding has been named dark flow. According to astronomers, there could be a dark flow or unobservable external forces originating in vast structures outside our universe that we are unable to fully understand. By studying the enormous clusters of galaxies, among the largest structures in the universe, scientists have discovered the flow. These clusters are made up of thousands of galaxies grouped together with extremely hot gas that emits X-rays. Scientists investigated the movement of the clusters by analyzing how X-rays interact with the cosmic microwave background, the residual radiation from the Big Bang. The temperature of the CMB changes due to the scattered X-ray photons, a phenomenon called the Sunyaev-Zel'dovich effect. A team of scientists led by astrophysicist Alexander Kashlinsky from NASA's Goddard Space Flight Center in Greenbelt, Maryland, discovered this effect after studying a huge catalog of 700 clusters separated from each other by a distance of up to 6 billion light-years. That is half of the universe. This effect had not been observed previously in galactic clusters. They compared this list with a CMB map from NASA's Wilkinson Microwave Anisotropy Probe satellite and discovered that the clusters were moving towards an area of the sky located between the constellations of Vela and Centaurus at about 32 million kilometers per hour. This speed differs from the outward expansion of the universe, which is accelerated by a force known as dark energy. Scientists discovered a very significant speed, and this speed does not decrease with distance. The flow that astronomers detect simply cannot be produced by matter within the observable universe. Scientists concluded that whatever is causing the movement of the clusters must exist outside our observable universe. While the theory of inflation predicts many strange aspects of the distant universe, few scientists predicted the dark flow. The structures of the dark flow could be a component of an unknown creation of higher dimensions. Surely you are wondering if things can get even stranger at this point. Well, the following potential theory is based on the physics of the early universe, just after the Big Bang. Our universe resembles a bubble. Beyond it can be found other bubble universes, all submerged in the multiverse, an infinitely energetic sea. The concept of a multiverse, which consists of worlds similar to ours but with some subtle differences, originates in two areas of theoretical physics. One comes from our understanding of the multiple branching possibilities in subatomic experiments through the lens of quantum mechanics. The other is more concrete and comes from our theories about the extremely early universe. However, we must start with the universe to reach the multiverse. The universe is everything by definition. It is the totality of all physical reality. If something exists, it is in the universe. However, we can begin to open the door to other worlds even with that definition, by realizing that light can only move at a finite speed and that the universe is only a certain age. As we have already seen, our ability to observe the universe is limited But that explanation gives us a very faint idea of the multiverse. In reality, there's more in the universe than we can observe, so there are more things out there. More stars, more galaxies, perhaps even more intelligent creatures than we could contact. All these things are in the universe, but they are definitely not part of our own observable world. Those regions outside our observable bubble of the universe still look and act the same as inside it. They're governed by the same physical laws, only with other combinations, but there the story does not have to music and. For now, our knowledge of the first moments after the Big Bang is limited. We know the basic picture. Our universe used to be much smaller and hotter. Today, it is considerably colder, and we have tested this fundamental theory through various studies. However, when we go back to the Big Bang, we reach a point where our knowledge of physics breaks down. The conditions of the universe, when it was less than a second old, were so extreme that there is not a single physical theory that can help us. However, we believe that the cosmos experienced inflation, an extreme transformation in its early stages. According to all available evidence, when our cosmos was only a fraction of a second old, it expanded rapidly to enormous proportions, growing by at least a factor of 10 to the 60th power. The rest of the Big Bang, when our universe was saturated with particles and radiation and gave rise to stars, planets, and galaxies, was set in motion by this inflationary event. This is where the multiverse comes into play. Perhaps inflation never stopped. Perhaps the universe is expanding at an uncontrollable speed all the time, but part of it separates and becomes calmer. What we call the universe is just a small bubble of the true enormous universe, constantly expanding and inflating. According to this theory of inflation, the universe is always expanding. It never stops expanding at a speed greater than that of light. A region simply slows down and separates due to a random quantum fluctuation. The rest of the world outside our bubble continues to do what it normally does and has simply stopped randomly, while our fragment or bubble of the universe has simply stopped expanding in comparison to the larger universe. Our portion is not alone. Different portions can also be randomly established and become a normal universe that expands quietly. For observers of any of those portions, the universe will seem to them to have had a Big Bang in the past, a universe full of matter and radiation and an observation limit, just as we see it. These portions or bubbles appear to be individual universes in this scenario of infinite inflation, separated from each other by a continuously growing extension of absolute nothingness. This multiverse, a collection of independent and distinct universes full of creatures, stars, planets, and people, each doing their own thing, is physically driven and potentially very real. In the multiverse, our universe is not the first bubble that arises, but simply one in an infinite chain of universes. Imagine a huge foam like the surface of a bubble bath. The multiverse is the foam itself, always expanding and forming new bubbles. Each of them works as a separate, independent universe. Each of these bubble universes exists within the same space-time structure. If you point your finger in any direction, there's another world out there, beyond an immeasurable distance, and beyond that, another, and yet more. There are an infinite number of worlds in the multiverse if this type of inflation never really ends. While it is possible that all those universes ended their local inflation in the same way, it is also plausible that, as each universe separated, it obtained a new set of physical laws that accompany it, with different forces and particles. Some of those universes would be incredibly similar to ours. Others could have failed and be full of emptiness. Some could be much stranger than we can imagine, and others could be exact clones of ourselves. If, and this is a big if, there's only a finite number of ways to organize all the particles in a given universe, then, with an infinite number of universes, there would be destined repeated copies. This implies that not only is there another universe out there in a random direction, but that, if you travel far enough along that line, you will find a duplicate of yourself doing exactly the same thing as you at this precise moment. All this is quite far-fetched, but difficult to verify. The problem is that there is no way for the bubbles of the multiverse to interact with each other. Although they are not related, they exist, so we cannot simply get on a rocket and travel to our nearest neighbor. However, there could have been some cosmic accidents in our remote past. Our universe recently separated from the flow, driven by the great inflation when it was younger. There is a small possibility that our universes momentarily overlapped before being irreversibly separated. If another bubble universe formed near ours, that would offer a way to test the multiverse, since the probability of it occurring is extremely low, although not zero. Unfortunately, there are still no indications in the observations of the wider universe to suggest that we have been involved in such a collision. Those experiments do not exactly support the multiverse theory, but neither do they rule it out. All that remains for us is our theoretical understanding of the early universe, which is based on theories rather than real knowledge. Our understanding of inflation is quite limited. We do not know what caused it, why it had the energy it had, or why it ended in our universe. We are not even sure if inflation inevitably leads to a multiverse or if our own calculations are incorrect. Music, another equally enduring enigma, is the concept of eternal recurrence or the cosmic cycle, the idea that the universe has been reborn and will continue to be reborn in an endless cycle. Although this idea originates in ancient religions and ideologies, it is also present in modern cosmology. It goes back thousands of years to the time of the ancient Egyptian, Greek, and Indian civilizations. The cosmic cycle was a deeply religious and philosophical idea in many cultures. In addition to being a cosmological concept, the idea that the universe is cyclical was frequently used to explain how life and death, growth and decay, and other natural cycles affect life on Earth. For example, in ancient Egyptian mythology, it was believed that the universe went through recurring cycles of creation and destruction, each lasting a certain time. In Hindu cosmology, similar cycles of creation, preservation, and dissolution known as kalpas are observed. This cycle is believed to never end, and that a kalpa lasts billions of years. Among the most interesting characteristics of cosmic cycles is the possibility that there is a recurring pattern in the universe itself over time. Several cyclical models have been developed, including the oscillating universe theory, a cosmological concept that combines the Big Bang and the Big Crunch into a single cyclical event. If this theory is true, then the universe in which we live exists between a Big Bang and a Big Crunch. According to the Big Crunch theory, the universe will stop expanding and begin to contract. The universe will heat up as it gets smaller. This can be seen as the opposite of the Big Bang. The universe will contract and heat up instead of expanding and cooling. Everything in the universe will eventually collapse into a single small point where everything began. The idea was that each Big Crunch would be followed by a new Big Bang, tracing an endless accordion of expansions and contractions. This description would only mean one thing. All the laws of physics will be thrown out the window for physicists, which is simply unacceptable. To make matters worse, some cosmologists even argue that the universe will eventually collapse on itself after reaching its maximum point of expansion, which would essentially lead to the same conditions as when we extrapolate back to the moment of the Big Bang. To solve this mystery, some scientists suggest that perhaps the universe does not reach singularity after all, but will return to a state of expansion due to the repulsive forces caused by quantum effects of gravity, an expansion or Big Bang after a collapse or Big Crunch, which is aptly called the Big Bounce. The bounce signals the end of one universe and the beginning of another. However, the probability of a Big Bounce or even a Big Crunch is negligible according to the most recent observations of cosmic microwave background radiation. The universe will probably continue to expand until it reaches its end in a great freeze or thermal death. Currently, measurements of cosmic microwave background radiation collected with the Wilkinson Microwave Anisotropy Probe are of great precision. The age of our universe has been determined with extreme precision using the same equipment. So, it is very unlikely that discoveries about the expansion of the universe in the future will differ significantly from what is currently known. However, a deeper understanding of a mysterious entity could change the odds, such as dark energy. We may have to put the oscillating universe theory on hold, unless its true properties are drastically different from what they now show in the model of conformal cyclic cosmology proposed by Sir Roger Penrose. Each eon begins with a Big Bang event followed by an expansion phase in which matter and radiation are diluted and cooled. Finally, the cosmic microwave background fades, and the galaxies recede as the universe enters a phase dominated by dark energy. Time loses meaning, and conformal risk scaling occurs as the cosmos approaches its final state of cold, disordered nothingness. The result is a cold, empty, and uniform universe that serves as the beginning of the next one. A conformal risk scaling is a stretching or contraction that preserves all relative angles. Penrose uses it because a conformal risk scaling can be used to turn something that has an infinite size into something that has a finite size. The infinite that is risk scaled is not only space, but also space-time. Both are risk scaled, and then the end of our universe is joined to a new beginning. Mathematically, it can be done perfectly. The most important thing is that this cyclical process suggests that there is no beginning or end of the universe, and that the observed large-scale structure is a normal consequence of this ongoing cosmic evolution. The possibility of obtaining observational evidence is one of the most interesting characteristics of this model. Penrose has proposed that the cosmic microwave background radiation could have round patterns called Hawking points, remnants of previous eras. These points, which are named after the physicist Stephen Hawking, are places where black holes that previously existed have disappeared and have left traces in the cosmic microwave background radiation. There is still disagreement in the scientific community about the accuracy of certain studies that suggest that they have found possible Hawking points in the CMB data. Others argue that more research is needed to support or refute the presence of Hawking points as evidence for conformal cyclic cosmology. The observed patterns may result from random or instrumental effects. The conformal cyclic cosmology model would significantly change our understanding of the universe if it proves accurate. The model offers a new perspective on the nature of time, the development of cosmic structure, and the destiny of the universe by proposing a cyclic structure instead of a unique origin. It also raises interesting questions about the role of information, causality, and entropy throughout the eons. Future research in this field is likely to focus on improving this model and searching for greater observational support. The James Webb Space Telescope is also providing useful information to test the predictions of the conformal cyclic cosmology model. Advances in theoretical physics, including the creation of a quantum theory of gravity, could help reconcile the model with other cosmological models. Penrose's theory of conformal cyclic cosmology differs from the Big Bounce theory in that the expansion in conformal cyclic cosmology is never reversed. In the Big Bounce theory, the universe slows and eventually reverses into contraction, then reaches a density high enough to begin expanding again in a new Big Bang. Recent discoveries in various fields of physics and cosmology have provided potential evidence of cosmic cycles, such as in the cosmic microwave background, which serves as a valuable tool for understanding the early universe. Researchers have found potential evidence of this model in the patterns of the CMB, which may indicate the presence of events from previous eons. Other enigmatic elements of the universe, dark energy and dark matter, have puzzled scientists for decades, but according to some theories, they could be very important in cosmic cycles, with dark matter possibly triggering the final contraction of the universe and dark energy causing its accelerated expansion. In addition, the detection of gravitational waves from the collision of black holes and neutron stars has opened a new window into the universe. Some researchers believe that studying these waves could reveal clues about the cyclic nature of the universe and help test various cyclic models. Whether it comes from modern cosmology or ancient philosophy, the concept of the cosmic cycle significantly impacts how we see the nature of the universe and our place in it. If the universe really follows an eternal cycle, this challenges our notions of linear time and the uniqueness of our own existence, and raises questions about the nature of time and the universe. In addition, research on the cosmic cycle and its possible implications for modern cosmology can shed light on the fundamental laws that govern the universe. The ancient idea of the cosmic cycle may be key to solving some of the universe's greatest enigmas. As our understanding of the cosmos increases, philosophers, theologians, and physicists have been fascinated by the idea of the cosmic cycle. The concept of a constantly repeating universe can provide new and important insights into the nature of existence as we continue to investigate the secrets of the universe. The higher dimensions of space are also a requirement for string theory, which postulates that what we see as elementary particles are actually strings of energy that vibrate in several more dimensions than we can see. According to those theories, the other dimensions are compacted or rolled up on themselves. So even if you found one of those new dimensions and embarked on a journey, you couldn't travel very far before returning to your starting point. But what if an extra dimension could hide an entire universe? A theory about the structure of a universe formulated in the early 2000s proposes that human beings could reside in a three-dimensional brain that surrounds a larger space with four spatial dimensions plus time. There could be another three-dimensional brain that houses another universe within that higher dimensional volume that could occasionally collide with ours. They called it ekpyrotic model of the cosmos, in reference to a Greek term meaning conflagration, alluding to the fact that each cosmic collision would result in the hellish conditions of the Big Bang and could explain the origin and ultimate destiny of our universe. In this model, the brains alternately move toward each other, collide, and then separate again in an endless cycle that goes from the Big Bang to expansion to the Big Crunch and back to the Big Bang. The structure patterns we see today in the cosmos, in the distributions of galaxies and clusters, originate in this model from the interaction between the two brains in the slow collapse phase before the Big Bang. Although the idea of proposing new universes and higher dimensions to explain the Big Bang may seem extravagant at first, there are good reasons why physicists take these ideas seriously. You have probably been deceived into believing that the standard view of the early cosmos is simpler than it really is. When you think of the Big Bang, the first thing that comes to mind is probably a singularity, an infinitesimal point of infinite density that contains all space and time and that suddenly explodes to create the entire cosmos. That idea became popular because Einstein's equations of gravity can describe a cosmos that begins like this and perhaps ends with a great collapse, a singularity at the end, but it doesn't work with what we see in our observations. We can see the afterglow of the Big Bang and the background light right on the cosmic horizon, which indicates that a simple evolution from a singularity to the incredible universe in which we live today simply does not make sense. The problem is that the cosmic microwave background, the remains of the Big Bang, is too perfect. It is identical with an incredible degree of precision. 1 part in 100,000 in all directions, the same spectrum, the same intensity, the same color, or given its microwave light frequency. That is problematic, since there is no justification for two places on different sides of the sky to coincide in that way. Even if everything started together wrapped in a singularity, the way it expanded outward should have introduced extreme differences in different parts of the early cosmos in the expansion stage of cosmic evolution. The regions that are currently separated from each other never had the opportunity to reach a common temperature on one side of the sky. The cosmic microwave background should differ significantly from the other. From what we have seen so far, inflation seems to fit well with our current paradigm and even explains very well the small fluctuations of 1 part in 100,000 observed in the light of the cosmic microwave background. But we do not have what anyone would call irrefutable proof that it occurred, nor can we say how or why it began or what drove it, and likewise, it is not entirely possible to be hit by another universe, not even in the inflationary scenario. Two bubble universes could collide at some point, leaving traces like bruises in the background light of the other. If inflation truly happened, the sequence of events that created our observable universe could have happened repeatedly in different parts of a much larger space, in a process called eternal inflation. The theory states that, while the larger background space is always expanding, inflation sometimes stops in a small part of it, causing that region of the universe to heat up and give way to normal cosmic expansion. As a result, small bubble universes identified by their distinctive post-inflationary background give rise to a type of multiverse. Astronomers have looked for these signatures, although they have not yet appeared. We will continue looking. The ekpyrotic model has been revised several times over the years, and the most recent version does not suggest cosmic collisions or higher dimensions. It resembles inflation in certain aspects. Instead of being driven by brain movement, it is driven by the evolution of a scalar field, a type of energy field that fills space, similar to the one that most physicists believe drove cosmic inflation. Even though it no longer requires large cosmic collisions, the ekpyrotic model still includes a transition between a collapsing universe and the Big Bang. The cosmic horizon that defines our observable universe is an insurmountable limit that we cannot see beyond, and unless our understanding of the structure of reality changes drastically, we can be sure that we never will. The expansion of the cosmos is accelerating, and anything beyond our horizon will move away from us faster and faster, and its light will never reach us. Although we may never be able to say for sure what lies beyond that frontier, all theories have in common that our observable universe is part of a much larger space. Whether that space contains a multiverse of bubbles, each with different physical laws, or is part of a constantly expanding cosmos of which we're only a part in a cycle, or if space extends into directions that we cannot conceive. We don't currently know, but we are looking for clues. The patterns in the cosmic microwave background light, the distribution of galaxies, and even experiments that test gravity and the behavior of particle physics are giving us a vision of the fundamental structure of the universe and its evolution in its early moments. We are getting closer to being able to tell our entire cosmic story. We can already directly see the fire in which our universe was forged, the moments just after its beginning. With the clues we are collecting now, someday we could follow the story to its end. Our understanding of the universe has evolved enormously throughout our own evolution. In fact, the beauty of science lies in how little we know currently. Some of the best minds in the world are investigating questions such as what the universe really is and what lies beyond, if anything. Like many mysteries, like Pluto, the truth is that it all depends on how we define it. Is the universe everything that exists, or is it something more limited, just another aspect of all that exists? Is there another one like it out there? There are an infinite number of possibilities, ranging from worlds within black holes to universes distinct from our own. One of the most intrinsic parts of being human is our ability to wonder, dream, and imagine. Thanks to this, we have several theories about what is beyond or larger than our universe, which coincide at least with certain current observations of physics and mathematics. The possibilities are endless as we contemplate the stars. Let us remember that our curiosity transcends borders. The universe, where the finite or the infinite invites us to explore, to seek answers, to dream, and to wonder. Perhaps the greatest discoveries await us beyond the cosmic veil.